Bismillah ar-Rahman ar-Rahim. Today we are going to do some exercises related to chapter 2 and 3 of your textbook, which is on linear programming. Let's see first discussion question. Suppose a linear programming maximization problem has been solved and the optimal value of the objective function is $300. Suppose a constraint is added into this problem. Explain how this might affect each of the following: the feasible region and the optimal value of the objective function. The feasible region, if we add a constraint, it's gonna either decrease or stay the same. If it stays same only if the added constraint is redundant. Suppose that the constraint added is not redundant, then of course the feasible region is going to be decreasing. Regarding the optimal value of the objective function, again the argument goes that if the added constraint is redundant, it will have no effect. However, if the added constraint is not redundant, then there is a chance that the objective function may stay the same or will decrease. Let's see this with the graph. Let's look at that. X1, X2. Let's say this is our feasible region and the corner point which is optimal is this one. If we add a constraint, let's say here, and the feasible region now is add a constraint here, and the feasible region is now this one, then the optimal point is still the same. It will stay the same. So our objective function, which was $300 after adding the constraint, will be same. However, if we add a constraint which is like this one, and our new feasible region is this one, then of course now the optimal point, which was previously in that previous feasible region, is no more there. Then we will have a new optimal, and that new optimal will be less than what was earlier. So if it was before, if it was $300 before, now it will be less than $300. So this is the correct answer to discuss this type of questions. Okay, let's see another problem here. The Electrocomp Corporation manufactures two electrical products, air conditioners and large fans. The assembly process for each is similar in that both requires a certain amount of wiring and drilling. Each air conditioner takes 3 hours of wiring and 2 hours of drilling. Each fan must go through 2 hours of wiring and 1 hour of drilling. During the next production period, 240 hours of wiring time are available and up to 140 hours of drilling time may be used. Each air conditioner sold yields a profit of $25. Each fan assembled may be sold for a $15 profit. Formulate and solve this LP production mix situation to find the best combination of air conditioners and fans that yields the highest profit. Use the corner point graphical approach. Now, what I'm going to do is I'm not going to solve the problems graphically, but we will just learn how to formulate. I suppose that once the formulation is done, you'll be able to draw the constraints and solve it with corner point method. So let's see this problem. We can first identify what are the decision variables, and it is clear that the decision variables are air conditioners and large fans, because it's saying that find the best combination of air conditioners and fans. So these are the decision variables that yields the highest profit, and this also tells us that this is a maximization problem. We define the decision variables. We say x1 is equal to number of air cons, and x2 is equal to number of large fans, and we also know that this is a maximization problem, so we say maximize. We say z is equal to, we have the air conditioner is bringing $25 profit, so one air conditioner is bringing $25 profit, multiplied by x1. This will, the total profit comes from air conditioners, plus 15 x2. This is our objective function, and then we have two constraints. We have a wiring constraint and drilling constraint, and we say that the wiring is 3 hours of wiring, 3x1, plus 1 hour of wiring is needed for each fan must go through 2 hours, 2 hours of wiring. So we have 2x2, and the total number of wiring hours available are 240. All right, and then we have each air con must go 2 hours of drilling, so we have 2x1 plus how much is the 2 hours of wiring and 1 hour of drilling. Each fan must go to 1 hour of drilling, so it is x2 less or equal to 140 hours of drilling is available to us, and that's it. I mean, this is x1 and x2 both should be greater or equal to 0. I'm not going to solve it. You can, if you like, you can make a table before writing down the constraints. We can write down the make a table, and then if you need that, you can do that, because it will make you comfortable. If it makes you comfortable, do that, draw a table. Let's go to next. Okay, so the solution is x1 is equal to 40, x2 is equal to 60, profit is equal to $1,900, the objective function. This is we are expecting from if we draw the if we graph this constraints and find out the corner points and work out at each corner point the profit, the maximum profit yield will be $1,900, and number of air cons to make is 40, and number of fans to make is 60. Here's another problem. Let's look at this. Billy Penny is trying to determine how many units of two types of lawn mowers to produce each day. One of these is the standard model, while the other is the deluxe model. The profit per unit on the standard model is $60, while the profit per unit on the deluxe model is $40. The standard model requires 20 minutes of assembly time, while the deluxe model requires 35 minutes of assembly time. The standard model requires 10 minutes of inspection time, while the deluxe model requires 15 minutes of inspection time. The company must fill an order for 6 deluxe models. There are 450 minutes of assembly time and 180 minutes of inspection time available each day. How many units of each product should be manufactured to maximize profit? Again, we can see that it is about maximizing the profit. We have two products to be decided, how many units of each product to produce. So the decision variables are clear to us. One is a standard model and another is the deluxe model. So we can define the decision variables. We can say x1 is equal to number of standard models and x2 is equal to number of deluxe models, and then it is a maximization problem. We say maximize z is equal to how much the profit is bringing. It is bringing the profit per unit on the standard model is 60 and the profit on the deluxe model is 40. So 60 x1 plus 40 x2. Subject to, we can see that there are 3 constraints here. The first one is the assembly, and another is the inspection. So we have we can make a table if you like. We say resources, and our x1 is standard model and x2 is the deluxe model, and we have these are the resources: assembly and inspection. And 20 minutes are used for assembly, 20 minutes, and 35 minutes are used for assembly for deluxe model, 20 minutes for standard model, and the right hand side or the total available are 450 minutes. And for inspection we have 10 minutes of inspection for standard model and 15 minutes for deluxe model, and the total available hours are 180. We have one more constraint, that is that we need the company must fill an order for 6 deluxe models. So if we may write this the whole thing, it will be z is equal to maximize, z is equal to 60 x1 plus 40 x2, maximize subject to 3 constraints are there: 20 x1 plus 35 x2 less or equal to 450, and 10 x1 plus 15 x2 less or equal to 180. And then the third constraint is that we need at least 6 deluxe models. So x2 should be greater or equal to 6. And then for completion's sake we can say x1 and x2 should both be greater or equal to 0. Although we have already x2 greater or equal to 6, but as we have this non-negativity there, we can just write it down. Okay, let's continue. Another problem 3, media selection. A candidate for mayor in a small town has allocated $40,000 for last minute advertising in the days preceding the election. Two types of ads will be used: radio and television. Each radio ad costs $200 and reaches an estimated 3,000 people. Each television ad costs $500 and reaches an estimated 7,000 people. In planning the advertising campaign, the campaign manager would like to reach as many people as possible, but she has stipulated that at least 10 ads of each type must be used. Also, the number of radio ads must be at least as great as the number of television ads. How many ads of each type should be used? How many people will this reach? Now we can see from this problem that our objective is not profit, not even cost, although the cost is given, but the objective is to reach as many people as possible. And we know that each radio ad is reaching 3,000 people and each television ad is reaching 7,000 people. So we have to decide about how many ads of each type should be used. So we identify these decision variables. The decision variables are, let's say, x1 is equal to number of radio ads and x2 is equal to number of TV ads. And then our objective function is to maximize Z equal to 3,000 x1 plus 7,000 x2. This is our objective function, and subject to, now we can see that there are some constraints here. First of all, we can see the budget constraint is there. The budget constraint is that the radio ad is costing 200 and television ad cost 500 and the total budget is 40,000. So we can say 200 x1 plus 500 x2 less or equal to 40,000. This is our total budget. This is budget constraint. Then we have constraint like that we at least 10 ads of each type must be used. So we can say that x1 is greater or equal to 10, x2 greater or equal to 10. All right. Another constraint is that the number of radio ads must be at least as great as the number of television ads. So we can say that x1 should be greater or equal to 2x2. There is no other constraint here. Then we just write down the x1 and x2 are greater or equal to 0. Again, this is kind of redundant because these x1 and x2 are already greater or equal to 10, but as a completion, because non-negativity is there, we just add these x1 and x2 both are greater or equal to 0. Again, we are not going to solve it. I'm just formulating it. You can do it either in Excel or QM for Windows to get your answers. But I prefer that also you do it with graphically by yourself, so that in the exam, if it comes, you have the ability to find out your find out the solution. All right. Here's problem number 4. A fabric firm has received an order for cloth specified to contain at least 45 kg of cotton and at least 25 kg of silk, but no more than 35 kg of polyester. The cloth can be woven on any suitable mix of two yarns, A and B. Yarn A is out of stock and only up to 40 kg is available in the local market. Material A costs $5 per kilogram and B costs $4 per kilogram. They contain the following proportions of cotton, silk and polyester. So this table tells us how much they give by weight: cotton, silk and polyester. The question is, identify and define the variables properly and formulate this as a linear programming problem to minimize the total cost of this order. Minimize. Now we will see what are our decision variables. Now the decision variables are not cotton, silk or polyester. Please note that. The company has to decide how much this suitable mix of two yarns A and B such that we buy them and mix them to meet the requirement of cotton, silk and polyester. So our decision variables are, let x1 is equal to number of kilograms of yarn A, and x2 is equal to number of kilograms of yarn B. All right, then our objective is to minimize the total cost. The cost of yarn A and yarn B are given, so we say minimize Z is equal to yarn A is costing us $5 per kilogram, so 5x1 plus 4x2 yarn B. All right. Subject to, now three constraints are clear. We have cotton constraint, silk constraint and polyester. So, and by weight each is given 30% by weight. So it is actually cotton. So if we say 0.3 x1 plus 0.6 x2, and it says this is cotton, should be at least 45 kilograms of cotton. At least is greater or equal to 45 kilograms. This is cotton constraint. If you like, you can write down cotton here. Then we next is the silk constraint, which is 0.5 x1 plus 0.1 x2, and it says again at least 25 kilogram of silk, so it should be greater or equal to 25. This is silk constraint. And then we have polyester, 0.2 x1 plus 0.3 x2, and now we see that it says but no more than 35 kilogram of polyester. No more mean less or equal to 35 kilogram, and that is polyester. All right, And then we have one more constraint. It says that yarn is out of stock and only up to 40 kilogram is available in the local market. Yarn A is X1 and it should be less or equal to 40 kg. So this is material constraint, we can say. And then of course we say that X1 and say X1 and X2 both greater or equal to 0. Okay, let's see another problem. Solve the following LP problem using the corner point graphical method. At the optimal solution, calculate the slack for each constraint. So we have the formulation given here, and we are asked to find out the solution by graphical method. Now you can see that here this constraint is a special constraint. That's why we asked you to make this do this exercise to draw this, because many students, they are, when they have to draw this constraint, they are stuck with that, how to draw that. It's very easy actually. You just have for any drawing any constraint, first of all you make it equality, and then you need 2 points to draw the straight line, because this is a straight line, it becomes a straight line equation. And one has to see also that x, y both are greater or equal to 0, which means the drawing should be only in first quadrant. I can show you the result here. You can see that this is the constraint we were talking about, x minus 2y less or equal to 10. This is the constraint here. All right, and you just plug in two values here for getting point. One point can easily be y equal to 0 and x is equal to 10. Another point can be give some value of such that it can be in the first quadrant. You can give x equal to 20 or 30 or something like that, and just draw a straight line, and that's it. I mean, another thing is that it's saying less or equal to 10, x minus 2y less or equal to 10. So one has to see that this constraint is active on this side, or is it active on this side. For that you just plug in, for example here x is equal to 0 and y is equal to 0, and this x minus 2y, x minus 2y is less or equal to 10. So if we put x is equal to 0 and minus 2, y is also 0, 0 is less than 10. 0 is less than 10. So we can say that this point is in the feasible region. Any point we can check for any point and see that if it satisfies this inequality, then the constraint is active on that side. So this is active on this side, and the other two constraints are of course not difficult to draw. And just to find out the corner points, we have 4 corner points here, rather 5 corner points, this, and this 4, and the fifth one is of course 0, 0. These slacks values also calculated. Once we have the optimal solution, we just put these values in the constraints to find out what are the slack values, because slacks are just when you make the equality, you can say For example, the first constraint 3x plus 5y, and you have plus S1 equal to 150. So once you have your value of x and y here, plug in those values, you get the slack. All right. For second constraint, slack is 28.75, which means that this constraint is not binding, and we have a value of slack coming 28.75, unused resource. Next problem. The Dean of the Western College of Business must plan the school's course offerings for the first fall semester. Student demands make it necessary to offer at least 30 undergraduate and 20 graduate courses in the term. Faculty contracts also dictate that at least 60 courses be offered in total. Each undergraduate course taught costs the college an average of $2,500 in faculty wages, and each graduate course costs $3,000. How many undergraduate and graduate courses should be taught in the fall so that total faculty salaries are kept to a minimum? Let's identify the decision variables. It says how many undergraduate and graduate courses. So these are our decision variables, and we are going to minimize that. And also the cost is given. Cost of each course is costing 2,500 undergraduate and 3,000 for graduate. So the objective function is not difficult to write. We can say minimize z is equal to, let's say x1 is the number of undergraduate courses and x2 is number of graduate courses. Then just write down the constraint objective function 500 x1 plus 3,000 x2. And then faculty, we have student demand make it necessary to offer at least 30 undergraduate. At least mean x1 greater or equal to 30, and we have and 20 undergraduate courses. So x2 should be greater or equal to 20. Faculty contracts also dictate that at least 60 courses be offered in total. So x1 plus x2 should be greater or equal to 60. That's it. We don't have any other constraint, so we can say x1 and x2 both are greater or equal to 0. Let's check it out. This is already solved here. Minimize the cost here. Okay, x1 is, we define the variables first, minimize the cost, and then this is the constraints here, and we have, this is the non-negativity constraint, and we can draw this and find out the feasible region. This is the feasible region here. We have shown in magenta color, and then we have only two corner points, this corner point and this corner point. Work out these cost, and the minimum cost comes at here at 40 undergraduate courses and 20 graduate courses. That's it. All right, the next problem is about sensitivity analysis. We have a company which is making tables and chairs, and it has two constraints, carpentry and painting and varnishing, and the table is bringing $70 profit and chair is bringing $50 profit. We already have the solution for that. Graphical solution is there. It says that if you see the graph, it says that make table equal to 30 and chairs equal to 40, and this is the corner point here. C is equal to 40 and T is equal to, this is T here, we can say that this is T and this is C. Alright. Now it says that find the objective function coefficient range over which the optimal solution point T and C will remain optimal, and find the right hand side range of the two resources. Let's go to the next slide and I will show you the how to find out the objective function coefficient range. So the formulation is given, and what we do is we want to find out the coefficient, for example the coefficient range of profit range of this table. So we can say that let's say Z is equal to, and instead of putting 70 here, we just put C1. C1 is the contribution margin of table, C1 into T plus 50 C. Then we just write down, find out the slope. T is equal to Z over C1 minus 50C over C1. Now we make the slopes for these two constraints, we make it equality and find out the slopes of these two constraints also, and just equate those to find out the range. So we say T, first constraint, T is equal to 240 over 4 minus 3 over 4 4 C. This is the first constraint. The second constraint is T is equal to 100 over 2 minus half C. Now just what you do is you just equate these slopes to find out the range over which this corner point is staying the same. So we say that minus 50 over C1 is equal to minus 3 over 4, and from here we get C1 is equal to 66.67, and then minus 50 over C1, if we equate to minus half for the second constraint, we get C1 is equal to 100. So we can say that C1 has upper limit is 100 and the lower limit is 66.67. and we can work out for the second coefficient as well, the range of that. Of course, I'm not going to do that. You can find it yourself with following the same procedure. Now regarding the quantity, the right hand side, okay, if I may erase this now, all this. Okay, let's erase it out. Okay, it's done. Now we want to find out the quantity, how much Q can vary on the right hand side, let's say of the Carpentry constraint. So we can say 4T plus 3C is equal to Q1, and we want to see how much Q can vary without changing the variable solution mix. Or another way of saying is to keep the same shadow price. We have here is, we look at it, we go back to the graph. I'll show you the graph here. Now here in the graph, the Carpentry constraint, we are looking at the range for the Carpentry constraint. The Carpentry constraint, if you see, if you move towards the origin, this yellow line, the point will come over here, which is 50. T is equal to 50, and this point is T is equal to 50, and of course C is equal to 0. The corner point will start moving, because if you are moving towards the origin, this Carpentry constraint, if you are moving towards the origin, which means decreasing the right hand side, of course the constraint with the same slope, but it will be moving towards the origin, and it will hit the corner point from here. It will start moving downward until it goes to this point. So where T is equal to 50 and C is equal to 0. What we do is we just plug in this value, T is equal to 50 and C is equal to 0 in the constraint. We get the range for Q minimum, Q1 minimum. And for maximum, we move this Carpentry constraint away from the origin, and when you move away from the origin, this corner point will start moving toward this side, and it will have this corner point y is equal to C is equal to 100 and T is equal to 0. So let's just do that. We have these points, T is equal to 0 and C is equal to 100 for maximum. So Q1 maximum will be, if we put these values here, we get Q1 maximum 300, and for minimum T is equal to 50 and C is equal to 0. If we plug in these values in the constraint here, in equation 1, we get Q1 minimum is equal to 200. So we can say that Q1 range is from 200 to 300. That's it. And we can do the same thing for painting constraint.